Good morning, everyone. I'm Zhang Kunqi from Marconis. It is my honor to present our proposed schemes, which discussed about how to enable training neural network on NVM-based system. This is today's outline. First, I will introduce some issues when the system adapts NVM-based memory on neural network while applying the training process. Second, the background and the motivation will be discussed. Third, RAM NVM-friendly Restrained and Approximate management design, which contains the NVM-aware FFT convolution, sparsity-aware convolution, and the Lucy update-aware labeling strategy. Fourth, a series of experience is introduced in the session. In the next session, the conclusion is to conclude all efforts on this paper. The neural network has been widely used in machine learning, which has a higher accuracy than other approaches, but it consumes lots of time to train the network. When the size of a model keeps growing, it could result in increasing the need on DRAM capacity and cost design issues. But the DRAM has the disadvantage with high unit cost, low density, and huge leak power. Recently, NVM is regarded as a permission solution to replace DRAM. Because of the NVM has the high density and the short read latency and nearly zero leakage power advantages. There are two overheads in convolution neural network. We take the VGG16 on neural network as example. We found that there are a bulk of computation on floating point. The overall percentage is 97.3%. The result, which is feature map and parameters, takes the memory overhead is 96.60%. There were three ways of convolution. First one is direct convolution. It reads 3x3 input data by 3 times sequential ring and apply dot operation with the kernel data to form a single element on the feature map. And the next time, it moves to the next snapshot and to form another element on the feature map. It means some data will be read again and again. It is really slow and inefficient. The second way of convolution is image-to-color approach. It scans the image to take the 3x3 input data into a single color. Even though the image-to-color makes the CPU to read data sequentially, but it had redundant data in the input feature map matrix. The computation of image-to-color is 144 for entire image computation. On the other hand, the memory consumption is 169. The FFT convolution extracts the input data into revised input data. It is because of the FFT function needs the input data be power of 2. On the other hand, to fulfill the same size with the input data, the kernel data padding 0. After applying FFT function on revised data, it will make those data transform from spatial domain into frequency domain. Then, perform the element-wise multiplication on the data which be transformed by FFT. We will receive the FFT feature map. To get the feature map in the spatial domain, it should apply the inverse FFT function on FFT feature map. The overall memory consumption is 137. On the other hand, there's still a computation overhead in the frequency domain. It is found that the number of multiplication on complex number is 3 times of real multiplication. But the effective memory consumption is still less than image to column approaches, and the computation ability is better than an image to column. On the other hand, the age input data will be discarded because the data should be power of 2. So the accuracy may be decreased slightly. This figure shows the bit flip accumulation is not even distributed in the training process. Let's run it. There are some bits will have the highly ability on the bit flipping. It is because almost the floating point is stored by the IEEE 754 32-bit floating points. To sum up, while replacing DRAM with PCM and combining it with FFT convolution will speed up computation and save energy, but it will also result in memory redundant writes and uneven memories. Therefore, the goal of our mechanism is to reduce the damage to memory and increase the lifetime of memory. Here, as we mentioned before, the FFT length must be power of 2, and the kernel data padding 0 means expand to 512. It needs to pad the 487 zeros. It is really power memory consumes. So we propose the NVM-aware FFT convolution. It split input into small size that is close to kernel size. It means the kernel only padding 0 to length, which is A by A, is 64. It only padded 39 zeros. So when the kernel don't need to expand to be as large as original image, the more kernel in the network, the more memory we can save. In particular, the data in the odd region will be symmetric complex conjugate to the corresponding data in the even region, and vice versa. Actually, we only need to store almost half of data after input and the kernel data are transformed into frequency domain. To further decrease the number of multiplication for improving the performance of the proposed NVM-friendly FFT convolution method, we then propose a sparsity-aware FFT convolution policy. The reloop mechanism usually adapts to resolve the gradient vanishing problems. We also apply it to reduce the computation of complex number. However, the sparsity-aware FFT convolution policy shifts the reloop before the bitwise multiplication to proactively reduce the computation of the complex number. The Lucy update ware labeling strategy is proposed to reduce the uneven distributed issues. It is found that the last bits are less important in the IEEE 754 standard. It is because the training process inherently tolerates some weight loss. The last bit will write one time only at the start update. It means it can reduce the bit flip When we reduce a bit flip, we can enhance the entire lifetime. Please follow this figure. When the we will assign a block for the training process. When the training process is always write the same size, the 32-bit. The last 8-bit we will write one time and never update. So it will accumulate the bit flip on here. When it reach the variable count 3, we will migrate this block data into the next block to make the variable count bit lower to prevent the too much number of bit flip accumulated on the same cells. On the other hand, when the block is reassigned due to the round-robin manner, it will restore the kernel data by shifting them to n-bit forward to make the distributed comes even. Let's discuss about the experimental setup. The FFT is the conventional FFT convolution method. This is the baseline we compared with. The NVM-FFT means the NVM-aware FFT convolution method. The NVM-FFT-SA, which adapts NVM-FFT with the proposed sparsity-aware FFT convolution policy. The LUWL is Lucy update variabling strategy. The parameter and setup of two investigated neural networks, which is the net and the CFARNet. The configuration of evaluated of PCM-based and DRAM-based memory. In PCM-based memory, the read latency is 48 nanoseconds. The set latency is 115 nanoseconds. The reset latency is 14 nanoseconds. The read energy is 2 picojoule per bit. Set energy is 13.5 picojoule per bit. The reset energy is 19.2 picojoule per bit. The endurance is 10 to the power of 8. On the other hand, the DRAM-based memory, the read latency is 30 nanoseconds, is equal to the write latency. The read energy is 4.4 picojoule per bit, and the write energy is 4.5 picojoule per bit. The overall endurance is 10 to the power of 16. Our proposed RAM design can effectively get 1.96 times and 7.69 times acceleration on the net and the CFARNet, compared with the conventional FFT approaches. It is because the proposed RAM design could eliminate the large number of padding zero in the FFT transformation process. Furthermore, we propose the design further reduce a huge number of redundant writes by programming the insignificant bit approximately and the important bit with smartly adapting the data compression write technique. Our proposed RAM design decreases the large number of redundant writes by minimizing the padding overhead and exploiting the symmetric data property in the FFT convolution process. It is found that we can reduce 65% data in the net and reduced 31% data in CyberNet. We observed that the bit number of RAM approach can be decreased by up to 98% compared to the FFT approach. The rationale behind such a great improvement is because with the support of NVM-aware FFT convolution policy and the Lucy update ware labeling policy, we effectively reduce the redundant bit flip by programming insignificant data approximately. Besides, although we program important data restrainedly, the data are updated only when they need to flip. How the proposed Lucy update ware labeling strategy affect on the lifetime result in the cooperating with the NVM-friendly FFT convolution method is also presented, and it is denoted as NVM FFT-SA plus LUWL. Because of the balance of uneven writes and the reduction of redundant writes, it is observed that the lifetime of PCM with adapting Lucy updating ware labeling policy on the NetFi and CyberNet is 2.37 times and 2.17 times to that of one without adapting Lucy updating ware labeling policy, respectively. Because of our proposed RAM design on PCM-based system could significantly decrease the number of redundant writes, we can compare our approaches with conventional FFT approach on DRAM-based system. We find that the energy consumption of our proposed RAM design in PCM-based system can be remarkable, reduced by up to 87% and 97% on the net and CyberNet. The validation accuracy of our proposed RAM design decreases less than 2%, since the data operating in FFT approach has to be the power of 2. Our proposed NVFFT design partitions the data into small pieces of FFT convolution, and thus there are less data needed to be discarded. This work is motivated by the dilemma of training neural network on conventional DRAM base due to DRAM's higher leakage power, low density problem. In this work, we proposed NVM-friendly restrained and approximate management called RAM to enable training neural network on NVM-based edge devices. There are 3 policies. First one is NVM-aware FFT convolution policy. Is to reduce the memory redundant write, which caused by kernel padding in FFT convolution. Second is sparsity-aware FFT convolution policy, is to reduce the number of multiplication to enhance overall performance. And third, the Lucy update ware labeling policy is to reduce the bit flip effectively and solve the problem of uneven distribution of bit flipping caused by training FFT convolution. In the end, the experiment result shows our proposed RAM design significantly accelerated the execution time of training neural network by up to 7.69 times and enhanced the endurance by 2.38 times. Okay, any question?